Hello there, this is another look at some differentiation, work on differentiation requiring us to solve what are commonly called maximum and minimum problems. And you can see just in the valley of this picture we've got a minimum point, and there you go. So we're looking at shapes like that when we find this minimum. And you might get a question which talks about it. You might try to model the shape of this hill in terms of some kind of quadratic equation, and it's not uncommon to see things similar to that. This is quite a famous problem. It's where you have a piece of card and it says originally, you'll notice originally, before I cut out the corners, I think it's 1, 2, 3, 4, 5, 6 down, and it's 12 across. If you go all the way across here, it's 12 across. 12 across the top, 6 all the way down. And what you do is you cut off a corner. And obviously, when you cut off a 1 centimetre corner, you can imagine this actually, because this is basically the net. So if I decide to cut off a 1 centimetre corner, just thinking what kind of cuboid it would give me. It's an open top box, so it wouldn't have a lid, but other than that, it would be, well, it was 12 across, I'll cut off 1 from each end, it must be 12 long. And it was 6, I cut off 1 from each end, it must be 4 wide. And when that folded up, it'd be 1 high. So you can see the volume of this cuboid, if you did it, it would be 10 times 4 times 1, which is 40 cubic centimetres. And the question, quite reasonably asked, is if you choose not to cut a 1 centimetre corner off, if you choose to cut off, say, a 2 centimetre corner instead, or 1.5 or whatever, what would that then be in terms of the volume? Would it be a bigger volume or a smaller volume? And so one way to think about this is, what if instead of cutting off a known amount, you say, well, I'm going to cut off an unknown amount, and you say, I'm going to cut off X from each corner. And this is what we're trying to think of. What if the cut-off was X in each corner rather than 1 like I just did? What would happen to the volume now? Obviously X could be 2 or 1.9, or I don't know what the best answer is. But by definition, since this was 6 and I cut off an X from each side, this is 6 minus 2X. And this was 12 across the side, but I've cut off 2 X's, so it's 12 minus 2X. And so when I write this, my volume is length, 12 minus 2x, times by 6 minus 2x, which is the width, times by x, which is the height. If we just work this out, multiply this out, so what do I get 72 minus 24x minus 12x plus 4x squared, but that's all got to be times by x. So if I times it by x and tidy up a bit, I'm definitely going to get 4x cubed as a 4. So that's that one done. I've got minus 36x, which gives me minus 36x squared. Then I got 72, so plus 72x. That's my volume. And I want to maximize my volume. I'm fairly sure it says maximize. Yeah, what would give me the maximum volume? So whenever you see those words, max or min, you think, oh, I'm going to differentiate then, dv by dx. That gives me 12x squared minus, was it 72x plus 72. And whenever you want to find the maximum, you should know by now, you set it equal to 0. Divide everything by 12 gives me x squared minus 6x plus 6 equals 0. Doesn't strike me as an obvious one that factorizes. Let's type this into my calculator. Menu A, polynomial degree 2. So I've got 1x squared, negative 6x, and plus 6. I could have typed in the first equation, it should give me exactly the same answer. That's not a very nice answer. It comes up with x to be 4.73. I think that's wrong. Or 3 minus root 3. And that's 3 minus root 3. Oh, that's much more reasonable. The reason why I didn't like the first one was I physically can't cut off 4.73 from each side. I think it says 4.73, but my second answer is 1.27. I think I can cut off 1.27. So I think this is impossible because it's only 6 wide. You can't. That's not happening. I think therefore this is the result. It said find the maximum. There was only one, so I think that's it. So let's have a look at my answer. This was the posh version. Oh, there's the graph. All right, yes, there's the minimum. That's my 4.73. 1.27. You can see it's about there. That seems to work, and it seems to give me a volume around 40ish. I think I cut off initially exactly 1, and it was exactly 40. It looks, if you go a little bit further, you get a slightly bigger volume. There you go, not much. It wasn't worth the hassle, perhaps. This is the posh method. That's what I got up to. There's the 2 answers I got. Oh, I did then differentiate it again to prove that it was a maximum point. Okay. Here's a second example. I want to enclose an area to grow carrots to keep out some rabbits. Okay. So presumably I'm going to cage off some land which I'm going to put my carrots into. I have a piece of netting which is 10 meters long. The area is to be a rectangular, and I want to enclose the largest possible area. One side won't need to be netted as there's a wall on one side. All right. So here's the picture of what I'm going to be doing, and obviously my dotted line, this is the wall, but this is my area that I'm going to need to net off, and then it says the whole thing is 10. So I suppose if I set this equal to x, and this is obviously x, then this would be 10 minus 2x. That works. And so therefore the area of my section here is, well, it's length times width, which is x times by 10 minus 2x, which is quite easy to do. A equals 10x minus 2x squared. What do I want? Do I want to maximize it, presumably? Yes, the largest possible area. So once again, I differentiate dA by dx, which gives me 10 minus 4x, which I set equal to 0. 4x equals 10, and you get x equals 2.5. So I now know how big to make my piece of netting. How, 2.5 down, presumably 5 across and 2.5 up. Now, is it a maximum? I suppose I should check that. d2a by dx squared would give me, well, I before had 10 minus 4x, it just gives me negative 4 when I do it, which is less than 0. This is one where you don't have to check, it's a maximum. So it's definitely x is 2.5. So that's the width. And the length, I think, has got to therefore be 5 meters. Oh, I've even calculated the area as well. And there's a pretty picture. Third example, the number of foxes in St. Helens increases and decreases over time. A model for the population of these foxes is given by this equation. But this is not unusual to be given a posh formula. Notice the two we've had so far, we've had to use the formula that we have had to create ourselves, I suppose. Whereas here, they've given us the formula and we don't have to create it. Where T is the number of years since 2010. Okay then. How many foxes were there in the population in 2010? Oh, this is quite a common question. It's very common to be asked what the initial number was, which effectively what this is. So I'm going to set T equal to 0, and when T equals 0, this implies that P equals, I'm just going to type it in. So, oh well, I don't have to do anything there, do I? You notice that will disappear, that will disappear, that will disappear. The only thing left will be 100. So presumably in 2010 there were 100 foxes. That's done. Use calculus to find the year in which the population was least and give its size. Now, first of all, notice the word calculus. Calculus is a posh way of saying you're going to use dy by dx. Okay. And the second thing I'd say is this time it wants to find the least amount. Now, have I got? Yeah, I've got it. So p equals 2t cubed. P equals 2t cubed. What happened there? Minus 19t squared plus 40t plus 100. Now notice I said dy by dx. Of course, this time we have to write dp by dt. Get the letters right. And if differentiated, I get 6t squared minus 38t plus 40. And what do I do with that? I set it equal to 0. You always set it equal to 0. And might as well I've got the calculator on here, so I might as well use it. Now what is it? 6t squared is negative 38 and it's 40. And it says t equals 5 and t equals 4/3. Now we don't really know if it goes which are the, probably one of these is a minimum and one of these is a maximum. We don't really know which one's which. So I'm going to find d2p by dt squared. And if I do that, I get 12t minus 38. And I can set that equal to, I'm going to substitute my values in here. I nearly went wrong there. So when t equals 5, this implies that d2p by dt squared, getting a couple of interesting symbols there, put 5 into there, I get 60 minus 38, which is 22, which is greater than 0. That's the minimum point. And just to prove it, when t equals 4/3, this should theoretically be the positive, the negative one. So that, let's just check. It's 12 times 4/3, which I think is 16, minus 38, which is minus 22. You do very often get plus and minus the same values. That's less than 0, so that's the maximum. And it did say find the time when it's at its lowest. I think it's at the least, and give it size. So when t equals 5 is its lowest, least number of foxes. And of course it did say after 2010. So 5 years after 2010 equals 2015. That's the year. How many foxes do they have? I'll just substitute 5 into this formula. When p equals, I'm just going to do it 2 times 5 cubed. So mode 1, new one. 2 times 5 cubed minus 19 times 5 squared plus 40 times 5 plus 100. 75 is what I've got. So at that point there are 75 foxes. Solution 100, so yeah, perfect. Here's an old exam question from the OCR exam. It says, first of all, very similar to that one we did with the rabbits. We've got x going down here, that's obviously x. How long is it in total? This time it's 20 in total. So by definition this is 20 minus 2x. And just note, having seen this example means I've got a head start already. So show that the area is this. So if I was doing this, area equals length times width, area equals 20 minus 2x times by the x, which is of course 20x minus 2x squared. Nice, easy 2 marks. Use differentiation to find the maximum. Well, dA by, what was it, dx. So differentiate, I get 20 minus 4x. So d equal to 0. X equals 5, I think that is. And if x equals 5, find the maximum value. I now sub this back in. When x equals 5, what was it? It was a equals, and this is my formula, of course, 20 times 5 minus 2 times 5 squared, and that's 100 minus 50. I reckon it's 50 square meters. Don't know what the answer is. 50, that's a good sign. 5, yes, and we got that. Look, we're going to practice these in class. The one thing you'll notice is this is very much a case of 2 types of questions. One, you have to form your own equation from a picture, from some piece of information, usually a shape of some description. Or 2, they give you an equation, a bit like that Fox's question where they say, here's the equation now, use this equation to find when it's maximized or minimized or something. So they're the 2 types of questions, and we'll practice those in lessons. Thank you very much.